Okay, it's a quarter to 2 on April 29, 2020, and we continue with the lecture course on multibody dynamics. Today's lecture is lecture number 8, and we're going to talk about rolling contact and non-holonomic constraints. Non-holonomic is a very strange, archaic word, but I will explain in a second. And why rolling contact? Well, but it's a very personal thing, I believe that systems with having rolling contact are always interesting. From childhood on, I always played with toy cars and scooters and bicycles and mopeds and cars and everything with rolling, skateboards, inline skates, everything with rolling contact shows very interesting dynamics. Anyway, that's the topic of today. Before we start that, we're going to do, of course, our Kahoot quiz, right? Kahoot. There were some problems with Kahoot, so hopefully everything is running again. Let's put this aside for a second. Yeah, Kahoot, where art thou? Here. Number 8, yeah. And we are very classic, right? Okay, also I don't like the sound. Okay, the first one coming in. Very good. Yeah, while you are logging into the Kahoot, I must say it's really unfortunate that we have this non-in-class thing, everything only online, because the whole purpose of the Kahoot is to have feedback and discuss, right? Discuss among your colleagues. You could use, of course, the chat in WhatsApp, but that's becoming very complex, and the same with the chat in YouTube. If you start chatting there, it's going to be chaotic. So yeah, I'm sorry about that. There's nothing much I can do about feedback now. 100 and yeah, so the number of players now exceeds a little bit the number of people watching, so that should be okay. So I propose we start the quiz now. Yeah. 5 questions again. First question, number of cuts you have to make. So you see here a scissor mechanism, and we want to model it as an open loop, and we have to do a number of cuts to make open loop structure out of this. And then the big question is, how many cuts do you have to make? What is the minimum number of cuts to make an open loop structure? Of course, you can make an indefinite number of cuts, but and take your time, I mean, we still have 60 seconds. From my point of view, the delay is 10 seconds. You have to answer now. Aha. So we need some feedback here, right? Because there's a little minority which has the correct answer and the rest is completely wrong. So let's look at the structure again. So it's a scissor structure, and it. Where am I? Not here. Yeah, it's a scissor structure, right? So a number of rigid bars connected by revolute joints, and the big thing is how many cuts do we have to make an open loop structure? Well, first of all, this is like a one closed loop, right? So you have to cut it here. But if you cut it, then still you have this closed loop. So you have to cut it here too. And still you have this closed loop. So you have to cut it here. So in total we made 1, 2, 3 cuts in 2 directions. So we made 6 cuts. Now, to be sure, let's do some calculation. If we do these cuts, we need 1 angle, 2 angle, 3 angle, 4 angle for this part, as an open loop structure. And for this part we need 1 angle, 2 angle, 3 angle. So 3 plus 4 is 7 angles. We made in total 3 times 2, 6 cuts. So 7 minus 6 is 1, so it should have 1 degree of freedom. And well, when you look with your mechanical eyes to this, you can say, oh yeah, that has sort of 1 degree of freedom. If I move this thing, then everything will move, and it's only 1 degree of freedom. If you want to be sure about 1 degree of freedom, just count the number of rigid bodies and the number of constraints, and you will come up to the same number. Okay, a lesson learned. Next question. Time response of the system is... So this is about last week's homework. This quick return closed loop system from homework 7. And there are a number of statements. Read them closely and think about what is the... There's only one real correct answer. Think about it. Take your time. Yeah, very good. So the system is both periodic, it's energy conservative, and it is deterministic. No chaotic dynamics. Very good. Third question. In each step of the Gauss-Newton process, you have to solve a set of what sort of equations? Indeed, the majority is right. So in each step, incremental step, you have to solve a set of linear equations. Of course, the whole problem is usually nonlinear, and you do have constraint equations, but the thing you have to solve is just a set of linear equations. Okay, next question. The matrix C plus is also known as, and please read closely. Indeed, the correct answer is pseudo-inverse. Okay, last question, and that's about this week's topic, the rolling contact problem. Which of the following statements is true? So you see two tracks in the snow which are made by a bicycle. Now there are 4 statements, and my question is, which of the following statement is true? Track A is the front wheel, track B is the front wheel. You cannot determine which wheel made which track, or a bicycle can never make such a set of tracks. Indeed, track A is the correct one for the front wheel. So for those who, so the majority is right, that's good. For those who do not know, so track A is a very more wobbly than the track B. So apparently, and then if we look at the bicycle, and here I have a small model of a bicycle, right? So this is the front wheel, and this is the back. So actually the whole thing is symmetric, only this frame is very short and this frame is very long. So the result always is that if you ride along, that the path of the front tire will always be more wobbly than the path of the rear tire, because the rear tire is trailing. By the way, there's also a way to determine which way did the bicycle go. And for those who are really diehards, from this graph, and I have a question which you may address later on in the Zoom or in the chat or wherever you like, on an email or WhatsApp. And my question is, how did the bicycle go? Did it go from left to right, or did the bicycle move from right to left? Okay, that's a surplus question which is not in the quiz, but for the diehards who are really interested. So, did the bicycle go from left to right, or did it go from right to left? Okay, that was the end, right? That was the 5th question. We have a podium, but usually you don't put in a name, so I don't know who's on the podium. And then I appreciate feedback. Yeah, there's no name with it, okay. I like to get feedback, and I want to view the report. That's okay, and I'm going to save the result. Direct download. And I'm doing it into the drive, which is always handy. Okay, yeah, this is, oh, wrong one. This was the report. Oh, no, it's okay. Okay, that having done, yeah, we're gonna leave the site because we have everything. Yeah. So now we go to our topic for today. Okay, let's put this a little bit here. Yeah. Okay, so today is a rolling contact and non-holonomic constraints, chapter 17 from the book. And the first thing I want to look at is I want to picture a wheel which rolls without slipping. So I picture a wheel which rolls without slip. So let's make the picture. Then so you could say, yeah, I have some disk, and the disk is rolling on some plane. Let's assume for now that the plane is the XY plane, that the Z is up, and here it's touching the ground, right? So ding ding ding, is it? And here, so this is what we call the contact point. And then of course the wheel has some velocity, and the wheel has some radius, right? And of course the wheel is rotating with some rotational speed, which I call beta dot. Now, for now, since we are doing 2D dynamics, I mean in general a wheel would roll in a three-dimensional world and would tilt, but in this case the wheel will always stay upright because we do the upright two-dimensional case. So upright 2D case. Or in other words, I can go to my projection, my 2D projection on the plane. So I can immediately look on the plane, on the XY, and this is the origin, and there I can draw the wheel, and let's give it some thickness, and here is the hub, right? Then here's the center of the wheel, it's a top view, and then let's assume for Pete's sake now that the wheel has some velocity, v. So in other words, this is an x dot and a y dot in this case, because we're working in the plane. Now I also said that of course the wheel is rotating with, as I said here, with an angular speed beta dot. Now in the plane, that would be a vector which is directed like this, and that would be the rotational speed beta dot. Let's put in the radius of the wheel. This is the radius r of the wheel. Now if we look at this velocity, then we see that the velocity has two components. It has one component which is along the direction of the wheel, and it has a component which is perpendicular to the direction of the wheel. And the direction of the wheel is of course, I haven't put it in yet, but that is of course the orientation of our body, and that's just phi. So again, we can this velocity we can decompose it into two orthogonal parts, this part and this part. So this vector I'm going to call the v alongside, in the direction of travel, and this I'm going to call this component. It's a component, it's a scalar thing. I'm going to call the lateral velocity. Of course, the position of the wheel itself is x and y, like with the rigid bodies we do in 2D dynamics, and as I said before, the orientation of our body is this angle phi. Now, from this picture, we can immediately see what the condition is for pure rolling. So the conditions for pure rolling are. Now, actually, we have two conditions. The first is that we want no side slip, or in other words, it means that this velocity should be 0, so v perpendicular should be 0, that's one. But we also want that the rotational speed of the wheel complies with the forward speed of the wheel. And so we want to have, how did I say that? Pure rolling in forward direction. And if we want that, then we say, oh yeah, then this forward speed should be equal to beta dot, the angular speed, times the radius, r. So these are actually, in fact, two conditions. But note that these are two conditions on the velocities. Conditions on the velocities. And that is an important thing, because up until now, when we wrote down constraints, we always wrote down our condition on coordinates, that pieces had to stay together, or that they had to be in contact with the plane, or but now we have them not in the coordinates, but in the velocities, and maybe also in the coordinates, but in the coordinates and in the velocities. Well, there's a funny word for that, and with a funny word we call those, we name those constraints non-holonomic, and that is opposed to, of course, opposed to holonomic, and then constraints, I should say, what? Constraints opposed to holonomic constraints, whereas holonomic constraints are the ones where they just are a function of the coordinates. Then we also have something with time, and that had to do with scleronomic or not. Now, if you want to know all those details, then please read the first part of the Advanced Dynamics book by Heike Valerie, because in that first part in Advanced Dynamics she explained all those different things, time dependent and not time dependent. Where does the name non-holonomic come from? Well, that's of course the first guy who investigated these rolling contact problems. And you would be tempted to say Euler, yes, but unfortunately that's not the case. It was Heinrich Hertz. So Heinrich Hertz was among the first who came up with this wording of non-holonomic constraints, and also who developed the whole mechanics and dynamics of non-holonomic systems. Why? Well, because Heinrich Hertz was very interested in contact problems, Hertzian contact and those things, so also rolling contact. Very interesting figure, Heinrich Hertz, tragic also, died relatively young, very smart guy. Let's continue. Well, most of you know Hertz from the frequency and not from the contact problem. Let's be specific. So we said we have these two side slip conditions, but we want to express those, of course, in our system, in our coordinates, right? So then we have to take a closer look again at the picture. So yeah, let me copy the picture again. I can do that. So I take this picture, yeah, and I duplicate that, and then I put the duplicate here. Okay, maybe, yeah, we can make it a bit smaller, but do I need to make it smaller? No, that's okay. So let's look at the picture. We had first the condition on the on the perpendicular velocity being 0. Okay, what is the perpendicular velocity? Well, looking at the picture, we say, well, this perpendicular velocity is a scalar thing, of course, and it is actually the dot product of this vector with this vector, right? So it is the dot product of the velocity vector, this guy, with some direction. And what is the direction? Well, if this is the direction of the wheel, then this vector has a direction of, in the x direction, minus sine phi, and in the y direction cosine phi. Or in other words, if you expand this with the x dot and the y dot, we get minus x dot sine phi, and I use the shorthand notation, right, plus y dot cosine phi should be 0. So this is our first non-holonomic constraint. Okay, the second one, that was the v in the direction of travel, is beta dot times r. So what is rv in the direction of travel? And again, it is a dot product of the current velocity times, but now the direction vector is this direction, right? Which is of course also with a cosine and a sine, so that's a cosine and a sine of phi. Or in other words, that is x dot cosine phi plus y dot sine phi, and that should be equal not to 0, of course, because we want a pure rolling. That should be beta dot times r, and that is our second constraint. Note that we suddenly have some extra coordinate in the system. So not only do we have a position and an orientation, but we also have this beta. So you could say that we have like a 2.5D system, right? So note we have an extra coordinate, and it's more like a generalized coordinate. Yeah, can I call it a coordinate? I don't know. Beta, making the system. Yeah, I always say 2.5D. I don't know if it really exists, the wording. But in other words, our center of mass coordinate vector is now x, y, phi, and beta. So those are our CM coordinates of our rolling rigid body. Rolling rigid body. Yeah. Okay, so that having defined, now we have these two conditions, but I really want to focus on this no side slip thing, because I want to look a little bit broader. I not only want to look at rolling contact of wheels, but also things like skates. Ice skating is pretty popular in the Netherlands, and there nothing is rolling, but you clearly have a skate on the ice, and the skate cannot move left and right, but can go back and forth. But you can even extend that. If you look at a ship going through the water, then there is some side slip, but most of the ship is going in the longitudinal direction. So it also, if you want to make an approximate model, you could say, a ship is like a skate on the ice, and we put a non-holonomic constraint on that it can have no side slip. And there are more applications. So the field is a little bit wider than rolling contact. So therefore, let's focus on the side slip. Focus on the side slip. Okay, focus on the side slip. Or in other words, the V perpendicular is 0. Now let's look again at that condition. So V perpendicular was, and now I have to copy it, minus x sine phi plus y dot cosine phi. Should be 0, right? Now, like we did in holonomic constraint, with a regular constraint, we're gonna define a constraint. So we define a thing called side slip. So we define side slip S, and I gave it a S1 because we also have a S2. And we're going to define that side slip S1 as S1 equals, and then again the same, x dot sine phi plus y dot cosine phi. And then of course you can do the same, of course, for longitudinal slip, but for now that's not so interesting. So this is like a skate, right? It's like a skate. And let's draw the skate. So and then we forget about the beta. That is also pretty convenient because the beta is a bit strange thing. Let's go back to 100%. Yeah. So a skate, and I usually draw it like this sharp, narrow thing, which has a tendency to go only in this direction. So this is this point. This is the skate on the ice. If this is the velocity, then this is what we call S1, the side slip. And again, we want the side slip to be 0. Okay, another way of then writing this constraint is that we can say, we have this constraint S1, and S1 is an S1 of, it's an S1 of the coordinates, xi, because we see here the phi angles in it and so on. Not the position, but it, for now, but it could be, and of the velocities, right? But there's something special with that dependency on the velocities. It turns out to be that S1 is linear in the velocities. If you inspect that, it's not quadratic or some strange term with a sine or a cosine in x dot or y dot or phi dot. It's just linear in the velocity. So we could write it as S1, and then I repeat that again as minus x sine phi plus y dot cosine phi. And in general, I can write that then as a S1 in our case of, yeah, as I said here, xi and x dot I. But a very special case is it's linear in the velocities. So it turns out to be, I can write it like this, like a matrix times a vector. And then the vector is this linearity in the velocities, x dot, y dot, and phi dot. By the way, phi dot doesn't appear in the equation, but that doesn't matter. X dot, y dot, and phi dot. And then the leading terms are minus sine phi. This is a cosine phi, and here we have a 0. Okay, so you could write this as a sort of a Jacobian matrix. So like S1I times x dot I. And note, there's no comma here. No comma. This Jacobian doesn't come from any differentiation, or it's because it's linear in the forward speed. I can write this linear equation as a matrix multiplication. So this is a vector and this is a vector. Okay, that's very nice that it's linear in the velocities. We like linearity because linear equations we can usually solve. That's handy. Okay, what are now the constraints on the accelerations? Because that is the thing which we finally need in our equation of motion, right? And the constraints are, well, we'll just take this expression and we differentiate it again. So I get s dot 1 equals, well, I keep this first constant. So I get minus sine phi cosine phi 0 times, and then I differentiate this with respect to time. I get x double dot, y double dot, phi double dot, plus, and now I keep this constant and I differentiate this one. And actually I can write that, yeah, in various ways, of course. One way is yeah, okay, let's first write it as a vector. So first differentiate this. Well, there's no x, there's no y, there's only a phi. So I get minus cosine phi dot times x dot. Then the second one is cosine phi. I get minus sine phi dot y dot. And the last is just 0. Plus 0. Now there's actually a rather neat way to write this, because it's what we call a bilinear form. It's a quadratic or bilinear form. So we can also write that in another form. S dot 1 equal, and I copy this, plus, and then I can write it like this, x dot, y dot, phi dot, transpose times a big matrix, a 9 by 9, and then x dot, y dot, phi dot. And then this big matrix, how does it look? Well, finally, the outcome of this is, of course, a scalar thing. That's clear, because this 3 by 3 times 3 is a vector, and then this vector times this vector, this transpose is just a scalar thing. Now, the only outcome should be something with x dot, phi dot, and x dot and y dot. So apparently, there's no x dot squared. There's no x dot y dot, and there's only an x dot phi dot with a minus cosine phi. Okay, then a y dot x dot was not there, y dot squared was not there, and then we had a y dot phi dot with a minus sign. And of course, phi dot x dot we already covered here. So this is a 0 here, this is a 0 here, this is 0. Now, as you can see, there's something strange going on. And you already saw that here a little bit. So although we have sine phi and cosine phi, we have no derivative with respect to phi dot. And that means that although you can write it now like this, s dot 1 is this s1I times x dot I double dot plus s1I comma j x dot I x dot j. you would think, oh, well, there's not much difference with a holonomic constraint, but note that this is not symmetric in I and j. Now, to complete, we usually write this term as a convective term, right? So that this S1 I comma j x dot I x dot j is the convective term, and the convective term, do I call it h or g? I don't remember. Well, let's call it h1, and in this case it is like here, minus cosine phi x dot phi dot minus sine phi y dot phi dot. Okay, so back to this non-symmetry, and there we need a little intermezzo on functionals, and that is the following. Now, when you look at this equation, so let's say intermezzo. Let's look at this equation again. So we have this s, I dropped the index for now, s1. So it's s is minus x dot sine phi plus y dot cosine phi. Now looking at this equation, you might think, oh, maybe there is some function which, when I take the time derivative, results in this constraint. Or in other words, he says this is non-holonomic and it's a constraint in the velocities, but if I'm smart, I can find a function which, when I differentiate it with the time, will result in this. So in fact, it's actually a holonomic constraint, and then I can solve everything with the toolkit which I have already now. Okay, so let's suppose there exists a function f such that, and then we should say f of xi, right, such that if I do f dot, I get s. Okay, or in other words, if I do well, the f dot is df dxi times x dot I. Well, if that is the case, then if we do the second derivative of the thing, s dot, we get f double dot, and we get, of course, r df dxi x double dot I plus r df dxi dxj x dot I and x dot j. But now we have a very strange thing going on, because looking at these derivatives, this should be symmetric. So that is symmetric with respect to I and j. But we already saw here that there's not such a symmetry. Because suppose, depending from this, we come to the conclusion that, oh, the df dx, oh, my thing drops out. Why does it drop out? Okay. This re-establish connection for now. Okay. Okay. Yeah, so apparently it doesn't always happen at the university, but also at home. It has something to do, of course, with wireless, which is dropping out. Okay, my argument. So again, when I look at this function, and apparently the derivative with respect to x, in our case, is minus sinus phi. And apparently if I look at this, then of this function, which I still don't know it exists, is the f dy is apparently cosine phi. Now watch what happens. So if I now take the derivative df dx d phi, oh, and by the way, the df d phi is, well, there is no phi dot here, so apparently that's 0, right? Okay, so when I now take the second derivative, so this one with respect to phi, I get, what do I get? Minus cosine phi. However, if I take this derivative, df d phi with respect to the x, I get 0. And that can be true because they should be equal. Should be equal, right? There is no order in differentiation, or there is no order in the path you take. Or in other words, f does not exist. And therefore, this S is a non-holonomic constraint. Okay, so end intermezzo. And looking at the clock, I would also say let's do the coffee break now, right? So, and after the coffee break we continue with deriving the equations of motion for a non-holonomic constraint mechanical system. Okie dokie. Let's stop the recording and let's